When a city decides where to place fire station, it isn't asking what's the cheapest location for one station. It's asking how many stations do we need and where, so that everybody in the neighborhood can be reached within 4 minutes. That question, covering all demand with the fewest facilities, is the set covering problem. And it shows up in ambulance deployment, police precincts, emergency warning systems, and distribution networks designed across the world. This week, we go beyond single facility models, where we solve problems where the goal isn't just finding the best location, it's to find the best set of locations given coverage requirements, budgets, and equity constraints. We'll cover 5 model types, each attacking a different version of that problem. First, let's talk from single facility to coverage problems. In previous weeks, we minimized total transportation distance for one facility. The answer was deterministic, weighted median or Euclidean centroid. Coverage problems are different. Instead of minimizing cost, we're asking a binary question. Is a demand node within a specified distance of a facility? Yes or no? And we want to choose facility location, so the answer is yes for as many nodes as possible. And for all nodes with such few facilities, as possible. The coverage distance parameter is set externally. In emergency services, it might be a 4 minute drive time in distribution. It might be a 50-kilometer radius. The math doesn't determine it. Management or regulation does. What the model determines is where to put facilities given their requirements. Set covering problems. The set covering problem is the simplest location allocation model. The goal is to find the minimum cost of set candidate facility sites such that every demand node is covered by at least one facility. So here are our inputs, as you see here. AIJ is to the candidate sites. FIJ is the cost of locating a facility site at candidate site J. XJ, 1 if the site J is selected, 0 is other. This is our decision variable. Our objective is to minimize Z, which is minimizing the total facility cost. Two things to note. First, the set of demand nodes I and the set of candidate sites J don't have to be the same, but often they are. Second, the AIJ matrix is pre-computed based on the coverage distance. If the distance from site J to demand node I is within decision variables, IAJ equals 1. So here you can see we have 6 nodes, A through F, as you can see here, with the distances between them. Setting coverage distance, DC, at 11 units, we compute the AIJ matrix. A cell is green if the site J covers demand node I. The objective function is to minimize Z, and each facility costs 1. So, solving the linear problem, the optimal solution is Z equals 2. Open facilities at C and D only. So let's verify. Node A is covered by D and node B. Node C by node C and node D by D. This is a small example. 6 nodes solved by hand or Excel. Real instances have hundreds of nodes and require each branch and bound or dedicated solvers. Maximum covering location model. The set covering model has 2 practical limitations worth discussing. First, the number of facilities it prescribes may exceed the budget. If the model says you need 40 fire stations, but you can only afford 25, set covering doesn't help you decide which 25. Second, set covering treats all demand nodes identically. A node with 50,000 residents gets the same weight as the nodes with 500. That may not be what management wants. The maximum covering location model addresses both. We fix P, the number of facilities we can afford, and maximize the total covered demand rather than covered nodes. As you can see here in our model, we are trying to maximize total covered demand, subject to these. The key insight, and this is worth pausing on, is diminishing marginal coverage. In the worked example, the bar chart shows that roughly 90% of demand gets covered when you locate about 50% of the required facilities. The last few facilities cover very little incremental demand. This is exactly where budget constrained decision makers should focus. Find that elbow point in the curve. Here, let's talk about P center and minimax problem. Covering models fix the coverage distance and either minimize facilities or maximize covered demand. The P center problem takes a different approach. In the P center problem, also called the minimax problem, we fix P facilities and minimize the maximum distance from any demand node to its nearest facility. Think of it as an equity objective. We want to ensure that no customer is too far away, regardless of how many customers are near. Two variants exist. In the absolute center problem, facilities can be replaced anywhere on the network, including on the arc in between nodes. In the vertex center problem, facilities can only be placed at nodes. The absolute center always gives us an equal or better objective than the vertex center, but the vertex center is easier to implement in practice. Here, you can see the parameters. Our objective here is to minimize W, which is the maximum distance. So now let's talk about the absolute one center algorithm. For the absolute center one algorithm on weighted tree, there's an elegant three-step algorithm. First, pick any node, find the vertex farthest from it, and call it E1. Second, from E1, find the farthest vertex in the entire tree, call it E2. Step 3, the absolute one center lies at the middle point of the unique path from E1 to E2. The vertex one center is the node closest to that midpoint in between them. In the worked example, start at node C and find the farthest node, which is G, so that E1 equals G. From G, find find the farthest node, H, so H equals E2. The midpoint of that path from G to H gives the absolute one center, 9.5 units from node E on the link connecting C and E. Now, for the absolute two center, we have three steps once again. Step 1, find absolute one center using standard algorithm. Step 2, delete the arc containing the absolute one center. This splits the tree into two disconnected subtrees. Apply the absolute one center algorithm independently to each subtree. The two results form the entire solution. Now let's talk about uncapacitated location allocation model. The model so far on coverage and distance. The uncapacitated location allocation model introduces cost explicitly and creates a trade-off between the fixed cost of an opening facility and the variable cost of shipping from that one facility to customers. Here are our notations. In this model, we are trying to minimize the fixed cost plus the variable transport cost. The linking constraint 6 is the critical one. It ensures that if facility I doesn't ship to any customer, no fixed cost is incurred. If it does ship, the full fixed cost F is charged. This is what makes the model a mixed integer program. Uncapacitated means there's no upper limit on how much any of one facility can handle. The model can assign all customers to a single open facility if that minimizes cost. Capacitated versions add an upper bound constraint. Now, let's talk about comprehensive location allocation model. The comprehensive model extends everything we've done to handle real supply chain complexity. Multiple products, multiple plants, intermediate warehouses, and multiple customer zones, all simultaneously. The objective minimizes inbound transport costs from plants to warehouse, outbound transport costs from warehouses to customers, production costs, and fixed variable warehouse operating all in one model. Let's bring it together. For all these, choose between the fast heuristic for large-scale approximation or exact solvers. When optimality is required, the greedy adding method is your first line of attack. Next week, we move on into product, process, and schedule design, the inputs that drive everything upstream of facility location. See you there.